two words of warning. Um, the first one is this is really not my domain, so I just want to illustrate some aspects that I think are interesting in here, but there are way better people to present this than me. And the second word of warning is those of you who saw the lectures in South Africa will notice that I am not playing these slides in the same way as I played them in South Africa. The reason for this is that I'm going to post this on YouTube, and if within a presentation in YouTube I'm playing other people's YouTube presentations, I'm not entirely sure if YouTube is very happy about this, so I'm going to not run any risks. For those of you getting this later, the slides that are available will have the videos embedded, and you can play the YouTube videos from the embedded slides. But here in this presentation, I'm not going to go over the movies. So what I want to do, and this will be a short lecture anyway, I want to spend a little time discussing what are ABMs, agent-based models, when to use them and when not to use them, and I'll go through a couple of examples. So the first question is, what are ABMs? So the vocabulary is a bit used sometimes in an interchangeable way, whereas they probably shouldn't. I would say in general now, a lot of people would consider ABMs to be different from IBMs, which would be individual-based models. Essentially now, I would say a lot of people think of IBMs as mathematical models that deal with problems at the individual level, which could be, for instance, continuous time Markov chains. But whereas agent-based models are more computational only models. But I have to say that the distinction between the two is not clear, and some ABMs might be IBMs and vice versa. So it sort of depends of the approach and etc. So another point that I would like to make is that ABMs are typically not like network models, which are models which endow vertices with simple systems. They essentially resemble metapopulation models, but where the constituting units have much simpler models. They can be ABMs. They can also be studied analytically with great effect. I am not in this course going into network models. This is another topic. First of all, that is not my specialty, but more importantly is worth an entire course. So I'm mentioning these as we go, but I recommend seeing other resources for this. So when can you use ABMs? So I would say for me, the main thing is that an ABM is a very valuable tool to try to decipher contact processes. When you think about the way we do models, which you've seen a lot in this course now, we approximate contacts, and I've said it several times during the course itself. Contacts are probably the weakest part of mathematical models. We approximate what they can be, and we can get into quite a lot of detail, but our description of contact is altogether a very sort of ad hoc very high level view of contact. And this is where agent-based models can be very useful because they allow you to look at the individual trajectories of individuals, agents. Um, and so if you have a good definition of contact, and I should point out that even in an ABM, contact is a model in itself, but it's a sort of lower level model. But if you have a good definition of what it is to be in contact, then you can have two agents come into contact with one another and you can detect this. And you can, because agents are individuals and they move sometimes, not all models do that, but they can move in space according to prescribed patterns, then it's easier to sort of understand what an actual contact is in this context. Okay, so I think this is really where ABMs are very, very powerful potentially. So they're very useful to understand, for instance, behavioral responses. So if you think about a population of individuals and they are doing some things and they react to a stimulus by a set of rules and also take into account what their neighbors do, well, that is very easily, well, more easily addressed in an ABM than it is in a classic mathematical model. So for instance, there are some well-known cases of ABMs where people have looked at panic, crowd movement, and etc. And this can be investigated this way. Another topic that is well suited to analysis with ABMs is, for instance, proper behavioral responses. So if you have a sort of mind model of how it is that people take decisions in terms of, for instance, vaccination, then it is possible to put this as part of the response pattern of an agent and see how a population of agents react to the introduction of a vaccine, for instance. Okay, so these are topics where ABMs are really, I think, extremely useful. There's also, in keeping with Fred Brower's, when you learn to use a hammer, every problem starts to look like a nail. There are cases where I think ABMs are not necessarily super useful. So one remark that I will make, for instance, is when you have a large number of effects happening often, sometimes you will have an emergent behavior, but oftentimes there won't be an emergent behavior and it will just be the behavior of the mean. If you end up in a situation where your model behaves very much like an ODE, well, you'd be better off using an ODE because the ODE is analytically tractable, whereas the ABM isn't. And that has been a default in some applications where people have made models for enormous populations without really worrying about the fact that altogether what was happening is some averaging of processes, which essentially was well approximated by an ODE. And there's another aspect that I would say with ABMs to beware a little bit is that you will see a lot of work by people in mostly computer science who are trying to develop a tool and trying to sell you this tool. But the problem is often that there's no real intent to use the tool for anything else than saying that a tool was produced that it would be interesting to use. And so there is a lot of literature around where people have developed a variety of ABMs for a variety of reasons, and that are not really investigating a proper epidemiology problem, but where people have essentially recreated an SIR model using a different tool from others that were created before. So beware. Sometimes it's good to use tried and tested and etc. programs because at least they have been used in a variety of contexts, and you know that they've proved themselves as good tools for investigation. Now let me briefly go through a bunch of examples. So I'm going to detail 3 models. One of them, the last one, is one in which I'm involved. The other 2 are earlier models. So one is about antibiotic resistance in hospitals. The other one is about effectiveness of contact tracing, and the one I'm involved in concerns hajj. So antibiotic resistance in hospital, this is a very interesting paper that's a few years old now. Oh, it's interesting. And it's about antibiotic resistance in hospitals. And that's, I would say, a very interesting, it's more an IBM than a proper ABM. But one of the very interesting aspects here is that it is a model where it is possible to derive approximating ODEs to the processes. And so this gives a very good confidence with the result, because you're able to analyze the results both numerically and from the ODE perspective. So the idea is the following. You have, it's essentially a hospital. There's patients entering and exiting the hospital. The patients are potentially infected by healthcare workers. Healthcare workers are also infected by patients. And I should point out, healthcare workers are transient carriers. They don't become infected per se, they become carriers. And if they wash their hands, for example, while they're carrying the pathogen, then the pathogen will go away. Okay. And so there's, they simulate days with 3 shifts, and the patients contact each other. So because the idea is, okay, how are patients infected? How is each patient infected, but also how does the infection spread in a ward, for instance? And there's rules for propagation, per contamination, per unit time. And so what you get are graphs like this. So I have a label here. So the status of, so these are patients, the number 1 and 2 and 1 to 4 are patients. Their status is they're uninfected in green. They're infected with the non-resistant strain in yellow, or with a resistant a strain resistant to antibiotics in red. And the line that you see here is a healthcare worker going from bed to bed. And so the line is plain if the healthcare worker is uncontaminated. It is dashed, well, first dotted if it's contaminated with the non-resistant strain, and dashed if it's contaminated, if a healthcare worker is contaminated with a resistant strain. And what you see here is a healthcare worker that deals with patient 1. While they're dealing with patient 1, acquires the non-resistant strain from them, because the patient is yellow at that point, then moves over to patient 4, who at that point is uninfected, but because they are manipulated by this healthcare worker that is infected with the non-resistant strain, they become infected with the non-resistant strain. Then that healthcare worker goes to see this new patient, number 2, who now is a patient that is infected with the resistant strain. They deal with that patient for some time, then they go back to see number 4. They spend some time with them, but this time they are not transmitting the resistant strain to them. However, when they go to patient 1, they transmit the resistant strain, and etc. Okay, so you can see how you can have activity like this described through time. You can repeat that for many healthcare workers, many patients, and so on. And actually, so on the left here, you see trajectories corresponding to one healthcare worker, for instance. So it's whereas this one is an average over 80 80 different trajectories. And what's interesting here is that this is these curves there that you see are what the ODE that they find to approximate the ABM predict. So you can see that the ABM and the ODE match quite well. So this, as I said, this is a very interesting example of a case where you can actually analyze the problem both mathematically and numerically. And you will gain some additional understanding of the process from using the numerics. Okay, I'm not showing a lot of the paper here, I'm just showing a few graphs, but so this shows you a first process. The second problem that I wanted to detail, and I'm going to be very, very quick here, is a model by some authors from mostly Saskatchewan, if I remember well, so nearby to Manitoba. And here it concerns the effectiveness of contact tracing in tuberculosis. And the reason why I want to show you this, so the previous model was a very simple model in terms of the potential states and the potential interactions. So essentially, a healthcare worker interacted or not with a patient. The patient had 3 possible states. The healthcare worker carried 3 or had 3 possible states: uninfected or infected with resistant or non-resistant strain. Here, this is a much more detailed process. And so here the idea, and I'm really not going to go into the details, but when you have patients that are diagnosed with TB, there's a lot of different surveillance mechanisms that can be put in place. So you see, for example, this represents someone who becomes infectious with active TB, and then their contacts are going to be identified, and then there are several, so some of them might be susceptible, so they have not contracted the infection. Some of them might be, I'm not sure what this one is, and some of them might be infected. Oh yes, uninvestigated contact. Okay, so these are some contacts that are tracked, some contacts that are not known, and some contacts that are infected with the disease. Okay, and the idea is to look at different scenarios for how you deal with the contacts themselves, how you handle the contacts, how thorough you are at following up on the contacts and so on, and to see what consequences this has on the disease. So you can see that here we have a much more complicated flowchart that describes the way contact tracing is initiated. And if you think about this in an ODE or even a continuous time Markov chain perspective, these are rare events we're talking about. I mean, there's not that many infections with TB, even in the TB-rich, high TB prevalence areas in Canada. And so, you know, writing an ODE for this would be not a very good idea. And also, there would be a lot of different compartments involved with potentially nobody in any of them. Whereas here, you have agents, and agents can be given different status and so on. And the model implements all of this flowchart, and it also implements, for example, so if you have a patient that comes in and they are investigated, and if they are detected as having active TB, then some different decisions are taken in terms of who to contact and etc. Okay. So this whole graph is easily simulated in a computer, whereas in an ODE, meh. And so what the authors do is they formulate scenarios, and you can see, for instance, is there any contact tracing? So if it's no contact tracing, then certain things happen. Or is there contact tracing? And then who's the contact tracing target? How much loss is there to follow up? So that's how many patients do you not see because they sort of disappear in the system. What's the priority that you choose? For instance, do you not make any priority, or do you say, well, I want to focus on people of a certain age, or I want to focus on people of a certain ethnicity, and etc. And you can do all these scenarios and run them. And then when you do that, you run all these different scenarios, and you can see how many cases of TB you would get over. So you see n equals 100. So there's 100 different simulations that are run for each scenario. And for each of these simulations, then you record the median, and then the interquartile, so that's the interquartile range of the numbers of TB cases that these different scenarios give you over the coming years. And as you can expect, for instance, if you're doing, remember the S0 was no contact tracing. Well, if you do no contact tracing, then that's where your worst outcome is. But then you can evaluate the different oh yes, I should here. You can evaluate the different outcomes of contact tracing scenarios depending on the situation. And the last model that I'll detail a little bit is deals with contact during Hajj. That's the pilgrimage, Muslim pilgrimage to Mecca, the yearly event. And now, if you have an event like Hajj, there's one of the important things in mass gatherings of this type is that you have a lot of people that come together from different countries. And in the case of Hajj, most countries in the world have people that come. Often not many, but there can be a lot. And if there is propagation during this event, there is a potential for this to act as an amplification, and after which dissemination would take infected cases back to places where there were no cases before. Okay, so understanding the dynamics of propagation during the event and potential mitigation measures is important. Now, one word before I get in, I'm quite fuzzy on the specifics. So this is what I understand about the process. And in a way, this is the understanding of the process in terms of a modeler. So what is it that that your model should incorporate? So the main sort of timeline of things is that pilgrims enter the mosque through several gates. They proceed to an area around this Kaaba, this cube. I have pictures later, okay? They proceed to this area around the Kaaba. They circle the Kaaba 7 times counterclockwise. And then when they are done with this, they do 7 trips between 2 locations that are still part of the mosque, but that are a bit further away. So in practice, this is what things look like. So this is the mosque itself, and then the Kaaba is this place here in the center. And so people counterclockwise rotate around this 7 times, and then I believe this is where they do the return trips back and forth. Okay, and you can see here this is an event during which there were quite a few people. As I said, I will not show the videos, but the videos are there that you can play when you're watching the videos. And this is to show you a difference. It shows the revolutions around the Kaaba. This was pre-COVID times, and then I put another video that shows you what happened during COVID times, because what happened is that the authorities decided that there would be social distancing, and you can see that people there are revolving around circles that are drawn, and when you watch that video you will see that. And likewise, this is what the trips between the 2 mounts looked like. That was in 2016. And this one, actually, you'll have to play directly on YouTube, but this shows the same process in a socially distanced version. And altogether, what's important here is that, except for these COVID times that are a bit specific, this is a very high density crowd. And the mixing patterns are also very specific. I mean, as you can guess, high density crowd, opportunities for transmission are quite high. But it's also important to see, well, for instance, what happened when when authorities imposed this social distance revolutions. And in that context, understanding contact patterns would help. And so what we have is we have a model. It's a 3D model here of the Kaaba here in the center, Mataf, so people will be turning like this, and then they'll be going between these 2 locations. And we describe this, and with a population of agents that follow the rules that say that they have to rotate 7 times counterclockwise and then proceed from here to there 7 times. And we can implement those agents, give them velocity and etc., and derive from this the nature of the contacts. So count the contacts, or count repeated contacts also. Is it always the same people that you're in contact with, or do you switch contacts? And all of this is something that can be investigated with this type of simulation mechanism, and that would fail miserably probably with an ODE. And so this is, for instance, the general setting in the social distancing case. And again, I'm not going to play these videos, but if you go there, this is videos by one of the participants to the project, where he's showing this video here is the path of an individual pilgrim, whereas this video here shows you what happens when you put 1,000 pilgrims together. Okay, and here he will be able to count the number of contacts. So you see here he's counting normalized contacts as the simulation progresses. So this was a very brief introduction to ABMs. As I said, this is not really my field. I might redo this video in a little later because I was investigating some mechanisms to use some of the some of the software that you can use to do to simulate agent-based models. I was looking at using this with R, and if I do so, I might add a little piece to this video. But in the meantime, this is where I'll stop.